After a brief introduction of second quantization and first quantization, today we are going to start the actual concept of this chapter. In the first concept, we will see the classical field equation. As you know that in the classical mechanics is dealt by two approaches. The first one is called Lagrangian approach or Lagrangian formulation of classical mechanics, and second one is called Hamiltonian formulation. So in this field theory too, there are two classical field equations. One is called Lagrangian formulation and another will be called Hamiltonian formulation. Okay. So we will divide the lecture on classical field equation basically in two parts. First of all, we will obtain the field equation on the basis of Lagrangian formulation of classical mechanics, and after that we will see the concept of Hamiltonian formulation for the classical field equation. Okay. But before knowing the field equation by Lagrangian formulation, we will have to know something about the coordinates of the field. You know, in classical mechanics, when we describe a system of particles, then the system is specified in terms of the generalized coordinates in Lagrangian formulation. Okay, and when you talk about the Hamiltonian formulation, then apart from the generalized coordinate, you also need the generalized momentum coordinates. But here we are first of all talking about the Lagrangian formulation. So as you know, in Lagrangian formulation, a classical system is specified in terms of the generalized coordinates. Okay. So when we talk about the field, then what will be the coordinates? Okay. This is a very fundamental fact to know before dealing with the problem of classical field equation. As you know, in Lagrangian formulation, you have definitely studied that the number of generalized coordinates to specify a classical system is simply equal to the number of degree of freedom of the system. If f is the number of degree of freedom, then you know there will be f independent variables to describe the state of the system, and that f independent variables are called generalized coordinates of the system. Okay, and those generalized coordinates in classical mechanics, you know, are represented by the symbol qi, where I actually runs from 1, 2, 3, so on up to f, where f is the degree of freedom. Actually, the basic difference between a mechanical system and a field is that the degree of freedom in case of a mechanical system is finite. As you can see, I have stated here that f is the degree of freedom of a classical system or a mechanical system. Here f is actually a finite number. This may be 1, this may be 2, 3, 4, 50 and so on. But it is never infinite. Okay. But if you are talking about a field, actually the field is defined as a physical system with infinite, that is uncountable number of degree of freedom. Okay. So you can say that a field is nothing. This is just a physical system with infinite degrees of freedom. Okay. So this is the basic difference in the description of a field and a mechanical system. If you are talking about a mechanical system, you have to consider the number of degree of freedom finite. But if you are dealing with a field, then the number of degree of freedom is simply infinite. Okay. When you say that the degree of freedom is infinite, it means the number of particles, number of particles contained in this system is infinite. Okay? In other words, you can say as the field has infinite degrees of freedom, it is just analogous to a system consisting of an infinite number of particles. Okay? Now, as you know that a system of particle is specified by the generalized coordinates like denoted by qi, where I runs from 1 to f. In fact, in the similar manner, if you are dealing with the problem of a field, then this field is specified by its amplitudes. If as a mechanical system is specified by specifying its generalized coordinate qi, in the similar manner, a field is specified by its amplitudes, and these amplitudes are denoted by the symbol psi of rt. Okay? Actually, at all points we define this psi. It means a field will be specified by the amplitudes like psi 1, psi 2, psi 3, and so on. In fact, here this quantity r, this r is actually continuous. It has actually a continuous value. Okay? Not a discrete value. So you can say that this amplitude psi of rt, which is defined for all points of the space in case of a field, is just equivalent or just analogous to the generalized coordinates in case of a mechanical system. Okay? In other words, you can say that the amplitude psi of rt play the same role in case of a field as the generalized coordinates qi plays in case of a mechanical system. Okay? In fact, this amplitude psi of rt are also known as field functions. These psi of rt, these are called field functions, and they may be considered as the degree of freedom for the corresponding field. So if n is the number of this psi for a field, then the degree of freedom of the system of that field will be n. But as I have told you that n will tend towards infinity, because in case of a field, the degree of freedom is simply equal to infinity. Okay? And as I have told you that the variable r is continuous and it must be considered as a continuous index. Okay? In analogy with a physical system, the field is the carrier of energy, momentum, angular momentum, and other observable dynamical quantities. Okay? Now, as I have told you that in this lecture our aim is to discuss the classical field equation. So, when you say field equation, what does it mean? Actually, what is this field equation? Actually, the field equations represent the relations between all the field functions psi of rt with their derivatives. It means when you will relate this psi of rt with their derivatives, then the expression obtained is called field equation. Okay? You can say that actually this field equation plays the same role in case of a field as the equation of motion plays in case of a mechanical system. So you can simply say that field equation is just analogous to equation of motion for a mechanical system. Okay. In fact, the field propagates in accordance with the field equations and carries with itself the dynamical variable. Okay. So these were something about the coordinates of the field. Now we will think about the Lagrangian formulation and try to obtain the field equation, okay, by Lagrangian approach. In fact, you will see that applying the Lagrangian formulation of classical mechanics, we will obtain the classical field equation, and these field equations will be obtained actually in terms of two parameters. In the present lecture, you will see that we will obtain the classical field equation by Lagrangian approach in terms of a quantity known as Lagrangian density. Lagrangian density means what? Lagrangian density means the value of Lagrangian per unit volume. Value of Lagrangian per unit volume, that is called Lagrangian density. It means Lagrangian divided by volume is called Lagrangian density. So this classical field equation is obtained first of all in terms of Lagrangian density, and then in the second part of this same lecture we will see the derivation of the classical field equation in terms of Lagrangian of the field, not in terms of Lagrangian density. But in this present lecture we are going to find the field equation only in terms of the Lagrangian density. Okay. Actually, if you will try to obtain the field equation in terms of Lagrangian density and then you will convert that equation in terms of Lagrangian of the field, that will be a vast lecture, that will take a long time. So for your convenience, I have divided this lecture in two parts. And as I have told you that this first part of lecture aims only to find the classical field equation in terms of Lagrangian density. Okay. Actually, you will see later on that we will denote the Lagrangian by the symbol this capital L. This is Lagrangian. First of all, note it. This is Lagrangian of the field. Okay. And we will denote the Lagrangian density by this curly L. Whenever you find this curly L in this discussion, you should think that this is not Lagrangian, but this is Lagrangian density, which means value of Lagrangian of the field per unit volume. Okay. And we will obtain the field equation in terms of this Lagrangian density in this lecture, and then in the consequent second lecture we will transform this field equation in terms of Lagrangian density in terms of the Lagrangian of the field. Okay. Now you know, in classical mechanics, whenever we try to find the equation of motion, okay, then we think about a very important variational principle which is called Hamilton's variational principle. It means you can say that Hamilton's variational principle is utilized to obtain the equation of motion, and so it is said that the Hamilton's variational principle gives the necessary and sufficient condition for formulating equations of motion. So here we will again try to obtain the field equation starting from the Hamilton's variational principle. And you know that Hamilton's variational principle is what? This simply says that the delta variation of the action variable is equal to 0. And when you say action means time derivative of Lagrangian L. And so according to Hamilton's variational principle, this delta is just a variational operator. Integral from t1 to t2 L dt is equal to 0. You have definitely watched my video on this Hamilton's variational principle in the playlist of classical mechanics. I will suggest you, if you have not watched my video on this Hamilton's variational principle in classical mechanics, you must watch it. And in the playlist of classical mechanics of my channel, you will get a concrete discussion, a detailed discussion of this variational principle. Okay. Now this variational principle, delta of integral from t1 to t2 L dt equal to 0, this holds under the condition delta qi t1 equal to delta qi t2 equal to 0. Actually, it means the virtual displacements at the end points, that is at the initial time t1 and the final time t2 is 0. So when these conditions hold, only then this Hamilton's variational principle will be satisfied. Okay. Actually, as you know that in case of a classical system, the Lagrangian of the system is actually a function of qi. It is also a function of qi dot and perhaps t. But if you say that we are talking about the Lagrangian of the system at a particular time, then you can say simply that Lagrangian of a classical or mechanical system is a function of qi and qi dot. In a similar manner, when you are talking about a field, then Lagrangian L of the field will be a function of the amplitude psi and psi dot. Okay. Here actually this psi dot qi dot represents the generalized velocity. Okay. And this psi dot is just analogous to qi dot. So this is the basic difference. At the place of qi, in case of field, we write psi. Okay. So you can say that Lagrangian of our field is a function of psi and psi dot. Okay. Now, as I have told you that in this lecture our aim is to formulate the classical field equation in terms of Lagrangian density, and I have told you that this Lagrangian density will be denoted by the symbol this curly L, and this is actually the value of Lagrangian per unit volume. Okay. And this Lagrangian density is actually a function of psi and all its derivatives. When you say all its derivatives, it means its derivatives with respect to the space coordinate and also with respect to time. When you say this L, curly L, that is Lagrangian density, is a function of psi, grad psi, you know, this is nothing, this is simply that derivative with respect to a space coordinate. This is del psi by del xi plus del psi by del y j and plus del psi by del z k. So this is actually the derivative with respect to the space coordinate x, y, z. And psi dot, you know that this psi dot is what? This is del psi by del t. This is derivative of psi with respect to t. And probably this t also. So Lagrangian density, you can say, is a function of psi, gradient of psi dot and t. Okay. Now, as a Lagrangian density means value of Lagrangian per unit volume. So, if you consider an elementary volume, in fact, if you consider there is a closed surface S enclosing a volume V, and in this volume V we consider an elementary volume, let us say dV. Okay, and the value of Lagrangian density at this elementary volume is this curly L. So as this L is the value of Lagrangian per unit volume, so Lagrangian of the field for this elementary volume will be what? This will be simply L dV. And when you will integrate this L dV for the entire volume, you will get the total Lagrangian of the field. Okay. So you can say that Lagrangian L of the field is equal to integral over V L dV. Okay. Or instead of this dV, you can also write d3r. Okay. So as L has been defined now in terms of the Lagrangian density L, curly L, so this variational principle which I have stated in this equation number 1, now you can express it in terms of the Lagrangian density curly L. So see here. Now the variational principle will be, this is just delta integral T1 to T2 L dt. As L you can see is equal to integral over V curly L dV, where curly L is Lagrangian density. So this expression can be written as integral of dt from T1 to T2 and integral over V delta L of psi grad psi dot T dV equal to 0. Okay. I think we have understand this expression. Okay. And as you know that this Hamilton principle is valid in classical mechanics only when the condition delta Qi at T1 and delta Qi at T2 both vanishes. Okay, it means at the end points positions are same. Okay, in the similar manner in case of field we simply say that the delta variation of the amplitude psi at time t1 and at time t2 both are equal to 0. So this is the condition under which this Hamilton's variational principle will be followed in case of a field. Okay, you can see that this equation is just analogous to the Hamilton's variational principle, and the condition is also same in case of a field. Okay. Now, as you know that this Lagrangian density L is a function of psi, grad psi, del psi means gradient of psi, psi dot and t. So from here you can easily find what will be delta L. Okay, as in equation number 2 you can see there this delta L is present. Since this Lagrangian density L is a function of more than one independent variables, so if your aim is to find this delta L, you must have to adopt the process of partial differentiation. Okay, so you can see according to the rule of partial differentiation, you can easily find delta L, and that will be what? This is del L by del psi delta psi plus del L by del, now this grad psi times delta of gradient of psi. Okay, plus del L by del psi dot times delta psi dot, and you can also write del L by del t delta t. But as you know, in case of this small delta variation at the end point, this delta t is equal to 0. So this term will vanish, and therefore I have not mentioned this term here. Okay, because delta L in this small delta variation, this delta t in this small delta variation is equal to 0. So this term has been not written. Okay. So delta L is this much. Now after obtaining this value of delta L, we will you can see some modification in this expression. Here you can see that in the second term there is delta of grad of psi. But you know that these two operators, delta operator and this gradient operator, may be interchanged, because the interchange of these two operators is permitted. So you can take gradient of delta psi instead of delta of grad psi. This can be written as gradient of delta psi. Okay, and this delta psi dot, this will be also replaced by, in fact, del t del t psi dot psi delta psi. See here. So this delta L is now written as del L by del psi delta psi plus del L by del grad psi dot grad of delta psi plus del L by del psi dot, and instead of delta psi dot it has been written here, this is del t delta psi. Okay. So after getting the value of this delta L, now what will be the form of Hamilton's variational principle, which you have written here in this equation 2. So replace this delta L by the expression which we have just obtained. So after replacing this delta L by the expression for it obtained here, what will be this equation 2? You can see this equation 2 now becomes integral t1 to t2 dt, and this is integral over v del L by del psi delta psi plus del L by del grad psi times grad delta psi plus del L by del psi dot del t delta psi dv equal to 0. So this is Hamilton's variational principle. Okay. Now we will actually evaluate the integral of the two terms in this expression. First of all, we are going to see the evaluation of the integral of this second term, that is del L by del grad psi dot grad delta psi. First of all, we are going to see the integral of this, okay, with respect to the volume. So you can see what will be this integral. This is integral over b del L by del grad psi dot grad delta psi dv. In fact, this volume integral may be written like this. This can be written as integral this can be written as summation x y z and triple integral. Actually there will be three, this volume element dv now can be written as dx dy dz. Okay, this will be written like this. So in this condition we will actually find if this gradient of psi, as you know that grad psi is equal to what? Grad psi has actually three components. So if we write only one component and then we take this sign of summation, the result will hold for the all. So this has been written like this: summation over xyz in double integral, and inside this square bracket I have written only the x component of this del L del grad psi. So this is del L this is integral del L by del grad psi x. It means this is x component of del grad psi. Okay, and for x component this gradient will be only del x. Okay, for x component, and here we take dx, and the remaining dy and dz written here. Now you can integrate this integral inside the square bracket by the method of integration by parts. Okay, so get focused on this integral which is with respect to x, and it is inside this square bracket. Here we will consider this del L by del grad psi of x as a first function, and del x delta psi as second function. And now apply the rule of integration by parts. So according to this rule, you know that this is equal to first function. So see here, I have written first function, del L by del grad psi of x. This is first function. And times integral of second function. What is second function? Second function is del x delta psi. And you know that integral of this del x delta psi will be simply equal to delta psi. No, you can write d dx instead of del x. So d dx delta psi dx. What will be this? This will be simply integral of differential of delta psi. So you can think that this dx will cancel out, and we will have only differential of delta psi, the integral, and that integral will be simply equal to delta psi. So first function times integral of second function. Okay. Now this dy dz has been written for this double integration. So this double integration and dy dx has been due to this. Okay. Now according to the formula, you know, in integration by parts, first function into integral of second function minus integral of differential of first function. And your first function is what? Your first function is del L by del grad psi x. So you can see I have differentiated del x has been operated on the first function. So this is del x del L by del grad psi x into integral of second function. Second function's integral is delta psi. Okay, and then dx dy dz. So instead of dx dy dz, here it has been written dv, and also this integral now is written as integral over b, because here there will be three integrals, one with respect to x and other two with respect to y and z. So it has been written here integral over b. Okay. Now as you can see that this delta psi, actually this first term inside this square bracket, this integral is actually a surface integral, because it has been it is going to be evaluated with respect to y and z, and this dy dz is just a surface element. So this double integral is nothing, this is just a surface integral. Okay, and you know that a surface integral actually vanishes because this psi is this psi either vanishes at infinity or it satisfies the periodic boundary condition, and that's why we simply say that this surface integral will vanish. Surface integral, because a surface integral is inversely proportional to r square, and when this r will tend to infinity, then this integral will vanish, this will become 0. And that's why we simply say that this surface integral inside this square bracket is 0. So only the second term left here, and therefore this integral is equal to minus integral over b. Now when you will apply this summation on this term, as here you know this term is for the x component, and when you will sum up all the components, that is x component, y component and z component, then this will be simply this del x del del x I plus del del y j plus del del z k, and this will be actually the divergence operator. So after summing up all these terms, we will have integral over v divergence of del L by del grad psi times delta psi dv. Okay. So this is the value obtained after integrating this second term. Now in the similar manner we will obtain this integral of the third term. You can see here this integral from t1 to t2 del L by del psi dot del del t delta psi dt. Our aim is to evaluate this integral. Let us see. Now here we will again consider that this del L by del psi dot is the first function, and this del del t delta psi is the second function. Again apply or use the rule of integration by parts. So you will write first function. First function means del L by del psi dot into integral of second function. You know, integral of second function. Second function is what? This is del del t delta psi, and its integral with respect to t will be simply delta psi. So this is del L by del psi dot delta psi, and limits are t1 and t2. Okay, minus integral of differential of first function. This is your first function, del L by del psi dot. So differential of first function means we will operate del del t on the first function, del L by del psi dot, into integral of second function. Integral of second function, that is del del t delta psi's integral will be delta psi. Okay. Now as you know that this term del L by del psi dot delta psi at the limiting points t1 t2 will be 0, because you know that delta psi at t1 and delta psi at t2 both are equal to 0. So at these two limiting points this delta psi vanishes, and therefore the first term in RHS of this equation will be 0. And that's why this integral, that is integral t1 to t2 del L by del psi dot del del t delta psi dt, this will be simply equal to this much. This is minus integral from t1 to t2 del del t del L by del psi dot delta psi dt. Okay. Now after obtaining these two integrals, we will simply use this equation 7 and this equation 6 in the Hamilton's variational principle, which has been defined in this equation number 5. So we have obtained the value of this term and this term, integral of these two terms, and we will substitute those values in equation 5. Okay. So after substituting those values in this equation 5, what will be our result? You can easily see. This integral has been written just at each. See here. Just it will be okay. The page is turned. So let us see. Okay. So this is integral of dt from t1 to t2, integral over v dv, and the first term is del L by del psi delta psi. Actually delta psi has been taken as a common factor, and minus the second term will be divergence of del L by del grad psi. You can see here this value. This is the value. Okay. And at the place of the third term, now we will write this minus del del t del L by del psi dot. Okay, and this is equal to 0. Now as you know that all the values of these delta psi's are arbitrary and independent from one another, because the amplitudes of the field psi 1, psi 2, psi 3 all are independent from one another. And so all these delta psi's will be independent from one another. So this definite integral will hold only when the integrand inside this square bracket will vanish, that will be equal to 0. So for the validity of this equation 8, you can say that the integrand which is inside these square brackets, that will be equal to 0. So let us equate the integrand inside the square bracket equal to 0. You can see that is del L by del psi minus divergence of del L by del grad psi minus del t del L by del psi dot equal to 0. Actually, this equation which we have obtained in terms of the Lagrangian density, this curly L, this equation is called the classical field equation. This is classical field equation. And actually, when you will compare this equation with the Euler-Lagrange equation, you know the Euler-Lagrange equation is in this form. This is d dt del L by del qi dot minus del L by del qi equal to 0. This is Euler-Lagrange equation. Actually, this field equation, which is in terms of Lagrangian density L, this is just analogous to the Euler-Lagrange equation of classical mechanics for a mechanical system. So this is just a field analogy of the Euler-Lagrange equation. Okay, but when actually we will convert this equation in terms of the Lagrangian L of the field, this equation is in terms of Lagrangian density curly L of the field, but when you will convert this equation in terms of the Lagrangian of the field, then you will see that the similarity between the Euler-Lagrange equation and this classical field equation will be more apparent. So in the next lecture, we will see how we can transform this classical field equation, which is in terms of the Lagrangian density, this curly L, in terms of the Lagrangian L of the field. And then you will compare that very equation with the Euler-Lagrange equation, and you will see that the form of that equation will be exactly similar. This form of field equation defined in equation A in terms of Lagrangian density, this is not exactly similar to this, not exactly similar, but when this will be transformed in terms of the Lagrangian of the field, the equation obtained will be just equivalent, just analogous, just similar to the Euler-Lagrange equation. So watch this video seriously, and then definitely watch the second video for the complete knowledge of the classical field equation by Lagrangian approach. Okay, so I hope you have understand the concept discussed in this lecture very well, and definitely you have enjoyed. So thank you very much.